it's time to start a new chapter. This is going to be chapter 27. And the title, Prime and Maximal Ideals. So what we want to do is go a little deeper into our study and understanding of ideals. And oftentimes I start a new chapter by just slapping a definition up there and then going with that. What I want to do in this case is actually kind of look, just sort of, I don't know, get some observations. And from those observations, those will motivate the definitions and so on that we have. So let's just say some observations. So, and these first come from last time. So let's say from last time, we were looking at, remember this one? So we were looking at R bracket X, and then we took a quotient of R bracket X, right? Now R bracket X, it's an integral domain, but it's not a field. Right? And then notice what we did. We took a quotient, so R bracket X mod, the ideal generated by 1 plus X squared, that turned out to be isomorphic to the complex numbers, which is a field. So we started off with something that was not a field. Yeah, it was an integral domain, but it was not a field. Took a quotient, and we got a field. So this is a field. So what did we do? Well, in some sense, by taking this quotient, right, we turned elements here that didn't have inverses, and we created inverses for them in some sense. Right? All right, so by taking this quotient right there, we took elements that were not units, and their corresponding cosets became units. All right, so something's going on there. We need to figure out what's going on. And so I want to compare this. So let's say now, consider what we're going to do is R bracket X mod the ideal generated by 1 minus X squared. Now, okay, so what do the elements here look like? Right, so a typical element is going to be polynomial plus this ideal, but using the same idea that we did before using the division algorithm. So applying the division algorithm, every coset in this quotient is of the form A plus BX plus the ideal. Well, maybe I shouldn't say is of the form, but every coset is equal to a coset of this form. So, right, so where A and B are real numbers. Right? So every coset, in fact, if you wrote down all possible elements of this form, right, all possible cosets, you would have a list of all of the cosets, all the elements in this quotient. Now, so I want to look at a couple of them. So note that if I'm going to multiply a couple of cosets here, so I want to do 1 minus X plus ideal generated by 1 minus X squared times the coset 1 plus x plus ideal generated by 1 minus x squared. And so if we multiplied this out, what we would get is, let's see, we'd get 1 minus x times 1 plus x, that's 1 minus x squared, right? And so that's equal to the coset here. Let me make a little more room here. So it's equal to 1 plus x squared plus the ideal generated, 1 minus x squared. 1 minus x squared plus the ideal generated by 1 minus x squared. But that's just equal to 0 plus 1 minus x squared, right? Which is 1 minus x squared. It's the identity coset in our quotient. Oh. And so, noticing that neither of these is equal to 0 inside the quotient, what we just did is we recognized, we've got 0 divisors here. So, what does that tell us then? This quotient, we didn't get a field, in fact, we didn't get an integral domain. Right? So, R bracket x mod, ideal generated by 1 minus x squared, is not an integral domain. And you might think, okay, well, what was special about this one compared to the other one? Well, okay, I mean, I'm not trying to hide anything, right? These are the two factors of that right there, right? So because we were able to factor 1 minus x squared, right, that allowed us, that enabled us to create a couple of 0 divisors. Okay, so something maybe about being reducible led to this conclusion right here. Okay. Okay. So there's one example, sort of motivating example. Let me look at another one. So next example or observation or whatever, Z is an integral domain. If P is prime, then when we look at Z mod the ideal generated by P, right, that's going to be isomorphic to ZP, which is a field. So, okay, fine. We started off with an integral domain, took a quotient that gave us a field. But if instead we consider some composite number, so let's say, I want to call it n or something. If n is composite, where, so here I want this to be composite, so both A and B are not 1 or n, so if this is composite, so A not equal to 1, not equal to n, which means neither is B, then in the quotient, right, so then Z mod ideal generated by n, we have, so A plus ideal generated by n times B plus ideal generated by n, that's equal to n plus ideal generated by n, right? That's the identity. So once again, we've got 0 divisors, right? Neither of these is 0, right? Because neither is a multiple of n, which means, all right, so we can say, Z mod ideal generated by n is not an integral domain. So, once again, when the thing generating our ideal factored, that enabled us to create zero divisors, right? So we got a quotient that was not an integral domain. Okay, so here's our first result of the chapter. So this is going to be theorem 27.1. And so it goes like this. So let's let R be a ring. We need unity, so a ring with unity. And let I be an ideal of R. If U, no, let's say not U, let's just say if I contains a unit, then I is equal to capital R. So there's kind of a, I don't know, curious result, right? As soon as your ideal contains a unit, that's all over. It has to be the entire ring, right? So it's sort of not an interesting ideal anymore. And so for the proof, so let's let, the proof is easy, so let's let U be an element of capital I, so this is going to be our unit. Okay, so then, let's see what we know. Well, so then 1, that's going to be equal to U inverse times U. Well, since U is in I, and I is an ideal, it's closed under external multiplication, which means that that has to be an I. Okay, so now, so notice what I'm trying to do. I already know, or here's what I need to do. I already know that I is a subset of R. I just need to show that R is a subset of I. So now, let's let little r be an element of capital R. So then, R times 1, well, 1 lives in I, and I is closed under external multiplication, which means that this is an element of capital I. Oh, well, let me write this a little nicer. R. That's equal to R times 1. That's an element of capital I because I is an ideal. Therefore, R is a subset of capital I, and that's all we need to complete the proof. As a quick corollary, so this is corollary 27.2. If F is a field and I is an ideal, then you only got two options. Either I is trivial or I is all of F. So fields have no interesting ideals, right? They have the trivial ideal and the whole field, and that's it. Okay, so why is that? Well, so the proof would go like this. I'm not going to write down the proof, but you can write down the details here. So let's see. Take an ideal. Take an ideal. If it's not trivial, then it has to have a non-zero element because we're in a field. Every non-zero element is a unit. So if it's non-trivial, it's got to contain a unit, which according to this theorem tells us that it has to be the entire ring, or in this case, a field. Okay, so now let's move on to a definition. So a proper ideal, let's call it capital M, of R is maximal if, so let's see, what we want it to be is somehow the biggest ideal of R, or at least a biggest ideal of R, which means, so that would mean, so maximal if there is no proper ideal of R that properly contains capital M. Okay, so let's say that. I mean, we've got proper quite a few times in this definition. So let's kind of rephrase this. So there's the definition, but we can say, in other words, M is maximal if whenever we have this situation right here, M contained in I, contained in R, where I is an ideal. So what's this definition say? There's no proper ideal that properly contains M. Right? So what we want is we can't allow, if it's going to be maximal, there is nobody that lies strictly in between these two. So anytime we have this setup, I either has to be M or has to be R. So where R is an ideal, whenever this either M equals I or I equals R. So it either goes that way or that way. There's nobody that lives strictly in between M and R. That's our definition, or that's how you want to picture, right? That's how you want to feel what a proper ideal is, right? You can never have this situation where you get non-equality in both cases, right? That will never happen. So as an example, let's let n equal to AB be, this is going to be an integer. Let's say it better. Let n in Z be composite. So what we would have is n equals A times B, where A not equal to 1 or n. Okay, so then let's look at this. So then the ideal generated by n is going to be contained in the ideal generated by A, which is contained in Z. Right? Why is that? Well, because A is equal to n times B. Right? So the reason, because n equals A times B, which has to live inside the ideal generated, right? So that tells us that little n lives inside here, which means that everybody has to live inside here. So let's see. What if this went the opposite direction? So if A was an element of the ideal generated by n, so what would that mean? It would mean that A is a multiple of n. So then A is equal to nk for some integer k. So what does that mean? It means that n divides A. Right, but that's impossible, right? So, right, because of our choice of, right, so since A divides, or, well, it really goes this way. Here, it's not impossible. But if n divides A, and we already know that A divides n, right, that would say that they're equal. But since A divides n, we have A equal to n, and that's a contradiction. Right? So what does that tell us? It tells us that this ideal is not equal to this ideal. So thus, n is a proper ideal of, or the ideal generated by n is a proper ideal of the ideal generated by A. This is usually my symbol. When I want to say proper, what I usually do is write contained but not equal to. So that means that it's a proper subset of capital A. Yes, I know some people say that that means proper subset, but it's really not universal, even though someone might have told you it's universal. Sometimes this refers to proper subset, sometimes it doesn't. So when I really want to be specific or explicit, right, I'll use that symbol to say I am talking about a proper ideal or proper subset. What else? So since n is, well, really absolute value, I guess, of n is greater than or equal to 1, every non-zero element of the ideal generated by n has absolute value greater than or equal to, what am I saying here? Oh, actually, strictly greater. Sorry, I screwed that up. Since absolute value of n is greater than 1, every element of absolute value, or ideal generated by n, has absolute value greater than 1. So what does that tell us then? So it follows that 1 cannot be inside the ideal generated by A, and so the ideal generated by A is definitely not equal to Z. So what do we have now? We have a situation, so let me put my symbols in here. We have a situation where n is properly contained in a proper ideal of Z, which means that the ideal generated by n is not a maximal ideal. Our conclusion: ideal generated by A, by n is not maximal. Okay, we've considered the case where n is composite. Now let's consider the opposite situation where we have a prime, right? So example, so now let's let P in Z be prime, and suppose I is an ideal such that, now here, so let me write this down first. So ideal subset Z. Now, what I'm going to do, I'm going to show that P actually is a max, or the ideal generated by P is actually maximal. Now, what does that mean when you have this situation? It means that I has to be one of the or the other, right? It's got to go either left or right, either equal to the ideal generated by P or equal to all of Z. Now, one way, it doesn't happen all the time, but typically what I like to do is suppose that it's proper in one direction and conclude that it's got to go in the other direction. So here's my setup then. Suppose I is an ideal that properly contains P. And what I need to do is show that I has to equal Z. Right? Okay, well, if we have proper containment here, then there is somebody in I that is not in the ideal generated by P. So let's pick, how do I call it, A, in capital I minus the ideal generated by P. So then, what does that tell us? Well, it means that the GCD of A and P has to equal 1, and so 1 is equal to AX plus BY for some X and Y in Z, right? Anytime, if the GCD is equal to whatever, D, then D can be written as a linear combination of those numbers. And that should not be a B, that should be a P. Okay, fine. Now, little p lives inside I. So does A. So since both P and A are elements of I, we conclude, right, I is an ideal. Since A lives inside, so does A times X, so does P times Y because P lives inside. So we conclude that 1, which is AX plus PY, is an element of capital I. By our previous theorem, so by, I think that's 27.1, I has to equal Z. Yeah, we got a kind of a tough theorem to prove, and so I'm going to save that for next time. All right, so we will see you then.